many times?
Of like the emergency alert
The same
system.
monthly?
Guess what? It's better to be tested than we don't know, right? All right. So the other component is the depends on the radius, and we call this would be the radial function. So you can that's our idea to solving for it. All right, and then we will come up the Hamiltonian operator, kinetic energy component plus the potential energy component. Now the kinetic energy component resides in the motion in x, y, z, and then you can express that in terms of r, theta, and phi. So therefore you will have an operation regarding with the variable radius, and then you have an angular component, and then you plus the potential energy. The electron is in the potential field with respect to the nucleus. Now I carry the z here. Z can be, we can call it atomic number. Now if it's a hydrogen atom, then Z is 1, but I put the Z right there just to say it's a generic one electron system. Okay, and then we can plug it into the Schrodinger equation right here. Now substitute the wave function with the radial R, angular Y function, and then we carry it out. As I showed, the separation variable, and we successfully actually can separate them. We have the angular wave function split into two functions. One represented by this blue equation. The number two is the splitting here. So you do, not all the mathematical function can be solved by separation variable, okay? But in this case, it does work. So therefore, the angular component of the y function really is the solution from the particle rotation on the sphere. So we will borrow that, all right? In that case, we have a whole table we learned from particle rotation of the sphere. It will have two quantum numbers, L and M sub L. L is the quantum number orbital quantum number. Okay, M sub L is the quantum number referred to the Z component, or we call the magnetic component. Now this is the solution. Guys, I can update that slides for you. Okay, this is the component for the radial component of the wave function. As you can see, we rearranged in terms of what we do. The first term related with the kinetic energy with respect to your function here, separated on the radial component, and then you have some sort of potential energy turn here and time the wave function r, then you have an E return to the wave function r on the right side. Okay, but I want to draw you guys' attention. Here the V is the V effective, okay? That's not the potential energy. The potential energy for the system is right here. That is the potential energy for the system. The effective potential, so when we say V sub EF, it's really when you regroup by solving this Schrodinger equation separation variable, including our original potential energy for the system, then plus whatever related with the separation variable that has a constant term here. All right, we group them together as a V effective. Now the whole idea, the reason we're doing that, if you really take a look at it in that kind of format, this looks like your kinetic energy operated onto the wave function. This looks like a potential energy like onto the function. This equivalent looks like a Schrodinger equation with the E and on the other side. So this is the effective potential. It's the sum of the potential plus this term here. Now, can you guys tell me on what source do we have this component, guys? Why do we have this? What do you guys think I would have this term? Because through the separation of the variables, we split into two equations, right? One is only equal to theta and phi, they equal constant. And then one is related with the radial component equal negative of constant. So the constant from the angular, how many times do they need to do that? Alright, so this is through the separation because there's one of the component equal to the constant, and that will carry through the constant in your radial part of the solution. That's why the L is introduced here. So you can clearly see the solution for the radial component will carry the L quantum number right here. Alrighty. Now, when we're solving for the Schrodinger equation, mathematically you will have generic solution. Now, how do we do in quantum mechanics? We're looking at particular systems. So we need to do one step further just to say, okay, I have a solution. Now you need to check, does it work? Or generic solution are applicable for our application system, or we need to have a constraint. Now, in quantum mechanics, we have boundary conditions. The boundary conditions restrict the solution for instance, the particle rotation on the sphere. You will have two quantum numbers to satisfy that boundary condition. Now, same thing when you're solving for this radial component of the wave function, it also have a boundary condition regarding with the variable r. So therefore, another quantum number is introduced to solving for that function, and that is the solution. So literally, this is your function, and introduce the boundary condition in terms of a radius r. And then here is the solution, not the exact solution. We will show you the exact solution, but this is what the solution of the radial component wave function looks like. And you can see the radial component only depends on the variable of r, but it has the two quantum numbers. The one is L, right here. L, clearly you can see in the function, you carry the L in the equation, that's what L is. And then we have another n quantum number. Okay, we had the n notation as a quantum number for translational motion in one dimension, particle in the box for one dimension 2 and 3, right? So that's the quantum number. Here we use the same n as a quantum number for the hydrogen atom, but that has a different name. All right. So this is skipping all the math. The solution for the wave function for the radial component of the part of the hydrogen-like system, it has four pieces. You will have the normalization constant represented by the capital N. Now you have a sub n and L to indicate this normalization constant is not the same for all the quantum state. Itself, it is a constant. Once you know what quantum state you're looking at it, but it depends on the quantum state. And then you also have the terms. You also have the terms regarding to the power of the r variable raised to the power of L. Now, L, right? So when we say the harmonic oscillator, this is the orbital angular momentum quantum number. Guys, what is the L value? L equals the orbital, the spherical harmonics, particle rotation on the sphere. What are the L values? L equals
positive integer over 0.
0. Okay, equal to 0, 1, 2, 3, 4. Now, how about m sub r? M sub r is constrained. By the value of L. Under each L value, the m sub L can take what? The steps go all the way from the negative L to positive L, then anything by a step of 1. Does that make sense? Okay, all right, but we already talked about this in topic 7F. Now here, go back to the radial function. You will have a term regarding the power for the radius raised to the power of F. All right, now, what else do you have? You have a polynomial function. Alright, and then the last one, then you have it says something in decay. That's an E function with a negative, raised to the negative power. Okay, so therefore it's complicated, guys. It's only a solution like this is super complicated. So the solution for the radial component has a normalization constant, has a power in R, and then you have a decay in R. So therefore you have a constant, power in variable R, polynomial in R, then you have an E function in terms of R. And then you say, no, wait a minute, that's not an R, it has a rho here. The rho here is a substitution with a constant that related with R. So if you take a look at it here, rho equals 2 times Z, Z is your atomic number, over NA times R. The reason they represented it in rho is to make that mathematical equation look simpler, okay? All right, and then A is your constant. A equals to m sub E divided by the reduced mass. And I said it how you can calculate the reduced mass, but considering you can calculate exactly what the reduced mass is, all right? Now, if the mass of the system equal to the mass of the electron, then the reduced mass equal to the A0. Now what is A0 then, guys? A0 equals to this expression, 4 pi epsilon 0 h bar squared over ME, mass of the electron times E as a constant, E squared. All right, now if you put all the numbers into this expression, E is your fundamental charge, equals to 52.9 PM. Okay, that's a picometer. So this is really the Bohr radius. If you guys remember in Gen Chem, we talk about the distance of the electron in the hydrogen atom. That is your Bohr radius. Now, for a specific hydrogen-like system, the A equals the ratio of the mass versus the reduced mass. You can calculate knowing the nucleus and the mass for the nucleus and electron. So you can calculate exact value A. So therefore, you can calculate the rho relationship with regarding to the radius. So that is the generic expression. Now, when it said that there are quantum numbers, so the total solution for the wave function, as we went through it in the lengthy detail, is that we went through this. So wave function, understanding the electron motion only, so you only have one coordinate corresponding to 3 variables. After solving for the Schrödinger equation, we will introduce 3 variables to satisfy the boundary condition with regard 3 quantum numbers to satisfy the boundary condition in regard to those 3 variables. Now this is a separation of a variable, so we successfully split into the angular component, which we already learned, and then we will have the radial component. All right, so each of the quantum state for that electron in the hydrogen-like system is determined by these 3 quantum numbers. Now we already know what the L and so L is. Now N is the principal quantum number. N is the principal quantum number. All right, by solving for the Schrödinger equation related with the radial function, we need to come up the principal quantum number not only for that, but we also come up with the value or what kind of values are allowed. So the principal quantum number equals to 1, 2, 3. All right, now as you can tell, when we're solving for this radial component, there is terms related with L. So the N will constrain the L quantum number, and the L quantum number will constrain the N sub L quantum number. So here we go. Basically, the quantum number N equal to 1. Now how does that constrain? L can take from 0, 1, 2, go all the way to n minus 1. Okay, now let's give it a shot. Let's say when n equal to 3, guys, what L value going to be? L can equal to 0, 1, and 2. Because the L values is constrained by n, so therefore it can take from 0, go all the way, it will have n values of L. So it starting from 0, go all the way to n minus 1, takes the integer. Okay, now the question I'm having is, how about m sub L? So m sub L is constrained by the L values. Do you guys agree with that? Okay, so when L takes 0, what m sub L value going to be? Very good. Oh, how about when L equal to 1? So negative 1. Okay, how about the L equal to 2? Negative 2, 0. Oh, let me do it in a sequence. 0, 1, and 2. Do you guys agree? Okay. Now, can I take one step further? Would you guys allow me? So in your JChem, do you guys remember the K shell, L shell, M shell for electrons?
Mm-hmm.
So we talked about the atomic orbitals. Atomic orbitals, right? So what do we do? 1s, 2s, 2p, 3s, 3p, 3d, right? It gets a little tricky when you go from here because sometimes the sequence between the 3d and 4s can be reversed. Are you guys following me okay? I'm looking at the atomic orbitals, alright? Now I'm not gonna go pretty far after this. After this is an increasing energy, but after the 3D and the 4S, at that region it gets very tricky. Even you put the ball, it doesn't really, follow a particular sequence anymore. So what do we call this? There's do we call this K shell? This is L shell. If you guys didn't talk about it, I'm telling you, that is your K shell, L shell, and M shell, and then N shell, and you can keep it going. You can use N equal to 1, 2, or 3, or you can represent it by the K, L capital letter. So now this really refers to principal quantum number N equal to 1, principal number equal to 2, principal number equal to 3. That's how we linked right here. Is it all good? I'm just link to what you learned in the JChem. When you think about this atomic orbital, right, you have the first 1s, only one atomic orbital. In the L shell, you have 2 or 3. Okay, let's do one step further. All right, now we have L values right here. So L can take 0, 1, 2, 3. We can use a lowercase notation to refer to L values. This will be SPDF. So if you take a look at it, this is your L equal to 0. That is your L equal to 0, L equal to 1, L equal to 0, L equal to 1. Then the D is L equals to 2. Are you guys following me okay? So then the atomic orbital, you really can refer to N to indicate which shell it is, and L to indicate what is the subshell. And then you have the sub right here. So that really pointing to, although you're like, oh, what the to. But I'm telling you, ultimately, those are the quantum states refer to those atomic orbitals that we learned in your JCAM. All right. Any questions on that? They're all good? Okay, all right. Okay, here we go. That is the table for the, now we already know the solution for the spherical harmonics. Now we show you the part of the radial component that we can resolve for. Now take a look at the radial component depends on the principal quantum number n and l. Alright, so therefore n can take from the positive integers 1, 2, 3, 4, and keep it going. That means the table, the textbook only give you all the way to the state of 3, so they don't want to get too complicated, but they have more. Alright, and then you will have a corresponding L values right here. I show you here, see, on the n equal to 1, that L can only take one value. Does that make sense? And then the n equal to 2, you can take L values on 0 and 1. Right? Because, and then when n equal to 3, you can take from 0, go all the way to n minus 1, which is 2. Okay, and then here is what we already learned from the spherical coordinates. Okay, in that case, guys, let's practice. I would say, what are the quantum numbers for this electron in the hydrogen atom that is at the 100? So this is the total wave function you have, but that equals to the 2 component, radial component, right? The radial component depends on n and m sub l. Oh, so n and l. So for this, what is the n value for the quantum number? What about the l? M sub l? Okay, very good. Then in that case, I will split into the product of the radial and the angular. So the radial will be 1, 0, and then times the angular component that depends on the quantum number L and m sub L. What would that be? Yes? Yes? Okay, now what will be the expression? This is, look at the table, 1, 0, that will be 2 times z over a to the power of 3 over 2, then times the e function, rho over 2. Right? And then that's your radial component from the table, from the solution. How about the angular component? So that is the exact solution for the electron in the quantum state 1, 0, 0. All right, now you may ask, a wave function in terms of variable object and phi, but the expression has a rho. And I said rho can be as a substitution for the radial variable r with a constant. The reason we do that is just make the expression much easier to look at. Okay. All right. Now I have a question for you. So for this particular ground state, it will be a ground state. Okay. For this particular function, what actually depends on? I have 3 variables, but in the exact expression, it only depends on the radius. Is that true? It only depends, for this particular quantum state, it only depends on the radius. Only depends on the radius. There's no theta or phi notation in the expression. Now, here's the math problem. Can you guys, so what is the variation? So we said the range for the radius is from 0 to infinity. Where's the 0 point? The 0 point is your nucleus, right? Yes, and the r is the distance for the electron with respect to the nucleus. Now, can you guys sketch this? Just mathematically sketch this according to the radius. So basically, can you sketch the wave function versus the r? Maybe just show one, instead of 3 dimension, let's just make it simple. I say here's the nucleus. This is your origin right here. And that's your r. That's the extension of r. Now here is your wave function here. Can you sketch what it looks like? You know the mathematical equation. Are you guys following me okay? Let's make this. Let's just make it simplified. It's in all dimensions, but I'm just only going to draw it in one line. That's away from the nucleus, which is at 0. This is increasing r. That is your increasing r. And this is your wave function. Can you sketch what would it look like? That's your solution. That's the solution, right? Yes. So what would be? So are you saying it is looking like that? Do you guys all agree? You guys all agree? Yes. Why is that? Because if you look at this expression, this whole thing is a constant, that whole thing is a constant. All remains is the e function. E is raised to the negative rho over 2, rho is your r, so it's an exponential decay with respect to the radius. So therefore, your wave function only depends on the r and the exponential relationship. That's why I'm looking like that. All right. Okay, we can have another practice. You can look at the, how about 300? 300 quantum state, then we look at the 30 for the radial component, it will be the expression like that. And 00 for the elements of L, then you're looking at the angular component of a root of 4 pi. And I think that concludes my discussion with how we're solving for this using mathematical trick, using separation variable, how we can derive the component, each component, then at the end, you piece them together, and how the quantum number will be introduced by imposing the boundary condition for each of the variables within its range. Any questions on that one? I know in the book, did you guys read this book? See how much that we went through and only covered in the textbook?
Yeah, it's just not that much.
Right? Who read it? No? Guys, do you read? It's only 2 pages. It's only 2 pages of material. Right? It's only these 2 pages of material, and that's about it. And I told you, I have a daughter in college. She's studying chemistry too, and physics and math this semester all together. I call her crazy, but she wants to do it, so never mind. A lot of times the same. She always say, "Mom, it's only half pages, but I have to spend like 2 nights to understand the whole half pages." And that's exactly what we are doing here in the textbook. It's just so simple, but the content involves a lot of things. So, all right, okay. Now we can take some notes. Once we have some mathematical equation, we can have so many conclusions onto it. Okay, you know, there's all based on the mass equation. So if you take a look at this, now we just dive in, talk about some notes about radio component. If you think about, we have this exponential decay component. If we include in that one, that will ensure the wave function approach to zero far from the nucleus. That's one of the boundary conditions when you have very far radius. And then the polynomial component, which is represented by this function here, it gives you the oscillations through the negative and positive component. Through that, you can also calculate the nodes if you want to. Okay, then you also have the power here. So you see, you have the power term, polynomial term, exponential decay. They have those three various functions already. Now, the polynomial term can actually, if I say, let's calculate about the nodes for that radio wave function. You know immediately, guys, this thing, this term, will not give you the node. Do you agree? Do you guys agree with that? This term will not give you a node. So if you want to know, although this is the whole thing is super complicated, but you know right away, this I don't have to consider. This I would not have considered because it will never approach to 0. So therefore, if I'm looking for nodes, which not only going to be 0, it has passing through 0, but you need to set to the 0. So the only thing can be 0 to start with is this polynomial term. Okay, so then if you look at this particular equation right here, all right, now let's take a look at this. If you look at, oh, maybe we look at this one. Look at this equation. Where is the power term? Of course, we have a constant right here. Now we have an exponential decay here. It's e to the power of rho divided by 2. That's your exponential decay term. Where is the power term?
Is
The
zero.
rho. Remember, rho raised to the power of L. Do you guys see rho raised to the power of L? L equals to 1. That's what on the rho term here. This in a parenthesis, that is your polynomial component. Okay, all right. Okay, so this basically they want to show you that with the solution looking like this, it really satisfies the boundary conditions in terms of the radius. Okay, now let's keep going. So when we look at the effective potential energy, okay, we can think about the effect. The system has a potential energy, it's in the Coulomb potential, but we remove through solving the separation variable the radial component, including the angular component of the potential energy, and we group them together and then become our effective potential. Okay, so if I would like to go back right here, when we're solving for this particular radial component of the wave function, and you guys see here, we make the expression in terms of being effective, right here, being effective, and then including the potential energy for the electron in the hydrogen atom, including the term that due to the angular rotation. So therefore, if we have evaluate this effective potential energy, it has two terms here. That is your Coulomb potential. The second term is the centrifugal potential. How many of you guys are using the centrifuge? Yeah, what happened? Or maybe we can go to like the,
Doesn't it separate based on density?
yep. So as a result of the spin, right, you also have this centrifugal potential, okay, the rotation. All right, so in that regard, what we can do though, we can plot the potential energy, it's a very potential, in terms of the radius of that electron with respect to the nucleus, and then we can sketch the plot. So the the effective potential depends on the radius. It has two terms. One is the Coulomb potential, that is in terms of the inverse relationship to the radius of the electron to the nucleus. Then the second component is related to the potential energy from the orbiting, which depends on the quantum number L, L plus 1, h plus squared over 2, reduced mass, and the radius squared, inverse of that relationship. Now we can examine the relationship of the potential energy with respect to the radius, the distance of that electron to the nucleus in two scenarios. Why in two scenarios? Because if L, whether it's a 0 or L is non-zero, that is a different scenario. You guys follow me, okay? If L is 0, what do we see? The effective potential is only half the Coulomb potential. That's it. Okay, now if we want to sketch a Coulomb potential, right? What is the relationship for the Coulomb potential? Inverse of what? The radius r, it has a negative value. So if you sketch that v in terms of r, it will look like this. It's all negative. As you increase the r, then the potential energy approaches to 0. Okay, so therefore, the effective potential curve will look like this. Now, if you have two terms, then it's a summation. It is a summation of both. One is from the potential field, the other one is from the centrifugal potential. Now you have to add up and see which dominates. Now, mathematically, guys, I think last time I called Zach. Zach is not around, right? I know he is here. Guys, trust me, I'm very smart and also I have a great memory. That's why I can say all these lecture notes without looking very much. I don't even need to read it, right? The textbook. And I can infuse all those. If you guys want to talk to me, you can talk for hours. I can talk so many different things. From math, physics, chemistry, from GenChem to quant, because it's all in my mind. Oh, that is a strength of me, that I can have things. If I see one time, call me one time. Or you guys come to my office one time. If you introduce to me, I remember. Okay, all right, Zach, what do you think? I have a two mathematical term for the effective potential. How do you evaluate mathematically for that curve? It's a math equation, right? Because you have terms. One is the inverse of r with a negative value. One is the inverse of r squared with a positive value. Now what would it look like? Now you have to think about it, which would dominate. So you are from 0 to infinity. How would that dominate? How would the balance go be? At some point it had to be 0, right? Close to 0, right? So if you really think about this, this is a positive value. It is in terms of a relationship of power of 2. It has a very strong dependence of the r. So the smaller the it is, the more positive number it is, and more steep increase of this look like. Or alternatively, you can sketch two of them and combine them together. One is 1 over r squared positive, one is 1 over r negative, and then you piece them together. So when the L is non-zero, that is the blue curve looking like, because of the contribution from both the Coulomb and the potential energy component. Okay, now you see there is this steep rise close to the nucleus, or close to when R is at small value, or close to the nucleus. That is because this term is dominating in that region. Make sense? Okay, alrighty, okay. Alright. Now we can talk about the energy aspect. I'm gonna put all this all together in one slide. So once we solving for the wave function, we can plug the solution of the wave function in back to the Schrodinger equation, and that's how we do it for all the system. And this is an expression for the energy. Okay, if we take a look at this, then the energy carries a negative sign. So that energy refers to the electron in a hydrogen one electron system, either hydrogen atom or one electron ion. So why it is negative sign? Does that make sense to you guys? The energy for the electron. It makes sense, right? Why is that? Because the electron is experiencing what? Attractive interaction. So the nucleus has a positive sign, the electron has a negative, so the electron is in the Coulomb potential, that is an attractive force, so the energy is negative right here. Now I group it into a bunch of a constant. This is your reduced mass, E is your fundamental charge, raised to the power 4, and it's 32 pi squared, then epsilon 0 squared, that is from your potential energy, then H bar squared right here. And then what you have is another, so this whole thing, so you have a negative, you have a constant. Then what you have it here, the third component is a z squared over n squared. So your energy is a negative, then you have the reduced mass, okay, then you have a z squared over n squared. Okay, now some textbook write this in terms of h. So then you'll have a different value here because h related with h bar divided by 2 pi. So that's fine. So be careful whether you have h here. If you have h here, then this value would be somewhat different. Okay, so if you think about this, so I would just think about it's attractive, constant, these are the variables. Now for the hydrogen atom, the energy for the electron, for the hydrogen atom, guys, Z equals to 1. Okay, so I carry the Z squared here in case we're talking about the other one electron system. Now, what is the relationship for the E sub n? It's really proportional to 1 over n squared. So that means, clearly, the energy only depends on one principal quantum number. So the wave function, the system can have a whole series of quantum states defined by those 3 quantum numbers. However, if you look at that energy expression, it only depends on the principal quantum number, n. So that immediately brings us a terminology. What is it?
Degeneracy.
Degeneracy. Okay, now what kind of fold? Once we have a degeneracy, then we think about 1 fold, 2 fold, 3 fold, 4 fold, 4 fold. Okay, so thanks for answering the question. Yeah, let's talk about this. So we can do some practice. This is tricky, very tricky. So n can start with 1. Then L equals to only have one value, right? L equal from only L equal to 0, and so L equal to 0. So you only have one quantum state, true? Under n equal to 1, you only have one quantum state. And then you only have one energy value corresponding is of 1. Alright, now what if n equal to 2 then? Then L equal to 0, L equal to 1, then the m sub L here equal to 0, and I'm going slow. You guys agree? How many quantum states here?
3.
So you have a quantum state 200. Oh. Okay, I don't think I lose a chocolate. Nobody said anything. That was terrible. Actually, use n equal to 1. The L can take 0 and 1. When L equal to 0, m sub L equal to 0. When L equal to 1, you will have a 3 m sub L values. Any questions on that?
No, I think what your first two was.
I think you're right.
Yeah, I think it was 2.
First end equation.
Well, yeah, because the first ends equal.
Oh, yeah. So what I was doing, okay, yeah, that is right. Oh, jeez. Okay. Does that look right?
2, 1, 1.
So 200 corresponding to this. 2, 1, negative 1. 2, 1, 0. 2, 1, positive 1. Yes? So then that all corresponding to energy of what? P2? Yes? Okay, all good, huh? Alrighty, let's do one more so we can see what the forward of degeneracy. Also as a practice. The next one is equal to 3. Then what do you have? L equal to 0, L equal to 1, L equal to 2. Let's get this out with you guys. Is it time already?
Yeah.
Okay, so you guys can practice, and I can give you guys a solution. It is an n-square fold. Because if you take a look at when n equal to 1 fold, when n equal to 2, you have a 4 quantum states. Then when n equal to 3, you will have a 9 quantum states corresponding to the same energy.